calculate the electrical load in amperes for a school using the optional method, you need to follow a few steps. Firstly, calculate the building load area. This is done by multiplying the floor area by the building load factor. For schools, the building load factor when using the optional method is 0.25 amps per square foot. So, if you have a school that is 65,000 square feet, you would multiply 65,000 square feet by 0.25 amps per square foot. This gives you a building load area of 16,250 amps. Secondly, adjust for the connected load. This involves multiplying the building load area by the connected load factor. The connected load factor is calculated by dividing the actual connected load in kVA by the building load area. If the actual connected load is 600 kVA, you would divide 600 kVA by 16,250 amps. This result can then be used to multiply the original building load area, which we calculated as 16,250 amps. Multiplying 16,250 amps by 600 kVA divided by 16,250 amps effectively results in 600 kVA. Thirdly, calculate the load in amperes. This is done by dividing the adjusted building load area by the voltage. Assuming a voltage of 120 volts, you would divide 600 kVA by 120 volts. Note that 600 kVA needs to be converted to volt amperes before dividing by volts. To convert kVA to volt amperes, you multiply kVA by 1000. So, 600 kVA becomes 600,000 volt amperes. Now, divide 600,000 volt amperes by 120 volts. This calculation yields 5,000 amps. Therefore, the calculated load in amperes, using the optional method, for a 65,000 square foot school with a connected load of 600 kVA, is 5,000 amps. It's important to understand the components involved in this calculation. The building load factor is a crucial parameter as it represents the electrical demand per square foot of the building. This factor can vary depending on the type of building and its intended use. For schools, the optional method uses a factor of 0.25 amps per square foot. The connected load refers to the total kVA of all electrical equipment connected to the building's electrical system. This includes lighting, HVAC systems, computers, and any other electrical devices. The actual connected load is usually provided by the building's electrical engineer or can be determined by summing the kVA ratings of all connected equipment. The voltage is the electrical potential difference that powers the building's electrical system. In this example, a voltage of 120 volts was assumed. However, it's crucial to use the correct voltage for the specific building. Schools often utilize various voltages, including 120 volts, 208 volts, 277 volts, and 480 volts, depending on the specific load and distribution system. Make sure to select the appropriate voltage for the calculation based on the specific load being considered. The optional method is a simplified approach to calculating electrical loads, and it is often used for general-purpose buildings like schools. It provides a reasonable estimate of the building's electrical demand based on its floor area and connected load. Other methods, such as the standard method, may be more accurate for specific applications or when dealing with complex electrical systems. Keep in mind that local electrical codes and regulations may require specific calculation methods or factors. Always consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and standards. For example, the National Electrical Code, or NEC, provides guidelines and requirements for electrical installations in buildings. It's important to follow the NEC and any local amendments when designing and installing electrical systems. The NEC provides tables and articles that specify requirements for conductor sizing, overcurrent protection, grounding, and other aspects of electrical safety. Understanding and adhering to these requirements is crucial to ensure a safe and reliable electrical system. In addition to the optional method, the NEC also provides other methods for calculating electrical loads. The standard method, for example, is a more detailed approach that takes into account specific load types and their demand factors. Demand factors are used to reduce the calculated load based on the assumption that not all electrical equipment will be operating at its full rated capacity simultaneously. The choice of calculation method depends on the complexity of the electrical system and the requirements of the local electrical code. It's important to select the appropriate method and to use accurate data to ensure that the calculated load is as accurate as possible. Once the electrical load has been calculated, it can be used to determine the appropriate size of the electrical service equipment, such as the service entrance conductors, overcurrent protection devices, and transformers. The service equipment must be sized to handle the calculated load safely and reliably. Undersizing the service equipment can lead to overloading, overheating, and potential electrical hazards. Oversizing the service equipment can result in unnecessary costs. Therefore, it's important to calculate the electrical load accurately and to select the appropriate size of service equipment based on that calculation. Electrical load calculations are an essential part of electrical system design and are critical for ensuring the safety and reliability of electrical installations. By understanding the different calculation methods, the factors involved, and the applicable codes and standards, you can ensure that electrical systems are designed and installed correctly. Always consult with qualified professionals and adhere to all applicable regulations to ensure a safe and compliant electrical system. Remember that the information provided here is for educational purposes only and should not be considered a substitute for professional electrical engineering advice. Always consult with a qualified electrical engineer or inspector for specific electrical system design and installation requirements. The calculation presented assumes a balanced three-phase system and does not account for any potential imbalances in the load. In reality, electrical loads may not be perfectly balanced across the three phases, which can result in additional current flow in the neutral conductor. The NEC provides guidelines for calculating the neutral load based on the unbalanced load conditions. Also, the calculation does not account for any future expansion or changes in a building's electrical load. It's important to consider potential future loads when designing the electrical system to ensure that it can accommodate future growth without requiring major upgrades. The NEC also provides guidelines for calculating spare capacity for future loads. Furthermore, the calculation does not account for any power factor correction. Power factor is a measure of how effectively electrical power is being used. A low power factor can result in increased current flow and reduced system efficiency. Power factor correction can be achieved by installing capacitors to improve the power factor and reduce the overall current demand. The NEC provides guidelines for power factor correction and its impact on electrical load calculations. Finally, the calculation does not account for any renewable energy sources such as solar panels or wind turbines that may be connected to the building's electrical system. Renewable energy sources can reduce the building's overall electrical demand from the utility grid. The NEC provides guidelines for integrating renewable energy sources into the building's electrical system and their impact on electrical load calculations. Therefore, while the optional method provides a simplified approach to calculating electrical loads, it's important to consider these additional factors and consult with qualified professionals to ensure a comprehensive and accurate electrical system design. Consider also that the NEC tables and articles are periodically updated to reflect changes in technology and industry best practices. It is essential to use the latest edition of the NEC when designing and installing electrical systems to ensure compliance with the most current safety standards. Always refer to the specific NEC article or table for the most accurate and up-to-date information. The process of calculating electrical loads is an iterative one, and it may be necessary to revise the calculations as the design of the building and its electrical system evolves. It is important to document all assumptions, calculations, and decisions made during the design process. This documentation will be helpful for future reference, troubleshooting, and maintenance. Keep in mind that this explanation provides a general overview of the process of calculating electrical loads using the optional method. The specific requirements and procedures may vary depending on the local electrical code and the complexity of the electrical system. Always consult with qualified professionals and adhere to all applicable regulations to ensure a safe and compliant electrical system. To summarize, the key steps for calculating electrical load using the optional method for a school are firstly determining the building load area by multiplying the square footage by the building load factor, which is 0.25 amps per square foot for schools. Secondly, adjusting the building load area by using the connected load factor. The connected load factor is the result of dividing the actual connected load in kVA by the previously calculated building load area. And thirdly, calculating the total load in amperes by dividing the adjusted building load area after converting from kVA to volt amperes by multiplying by 1000 by the voltage of the system. Using this method, one can find the calculated load in amperes needed for the example school.